Welcome to this lecture series in group theory. In this lecture, we'll see another application of the orbit stabilizer theorem. And what we will do is we will count the size of this group. This group is the set of all the n cross n invertible matrices over the field Fp. Fp is the finite field of size p. P is a prime. Okay, so let us recall some basic things. So if F is a field, then this is a notation to mean all m cross n matrices over F. This is a notation to mean all n cross n matrices over F. So when I say matrix over F, it just means the entries of the matrix are coming from F. Okay, and this notation is for all invertible n cross n matrices over F. So those are some notations. And here is a criterion to check if a given n cross n matrix is invertible. So that happens if and only if the determinant of the matrix is non-zero. Right. So we will need all that, and we will also, of course, need the orbit stabilizer theorem, which is what we are trying to illustrate the use of. So if G acts on X and little x is a member of capital X, then the cardinality of the orbit of X is the index of the stabilizer of X. So that's the orbit stabilizer theorem, and now let us get started. So this is the theorem that we want to prove. If P is a prime, then the size of the group of all invertible n cross n matrices over Fp is this number. So we have an explicit formula. And before we proceed, we need to recall one fact from linear algebra is the following. So suppose we have two 2 cross 1 matrices over F, then these are linearly independent. Linearly independent, and we can talk about linear independence of such things because this is essentially F2. This is essentially F2. It's just another avatar of F2. When we say F2, we just write things in 2 coordinates. Here we are writing columns. I mean, it's just that. That's the only difference. So this is a vector space. You add two such things, you get something of the same type, and you can scale things here from scaling from the scalar field F. So this is a vector space, and hence once we are given two things, we can ask for their linear independence. And from linear algebra, we know that these are linearly independent if and only if the matrix that you get by just putting the two columns side by side is invertible, which is to say that its determinant is non-zero. So that's a simple fact. And the general form is that given n things in mn cross nf, mn cross 1f, these are linearly independent if and only if this matrix A11, basically this Aij. So the ijth entry is Ai comma j. This n cross n matrix is invertible. So we know this from linear algebra. And now let's go to the proof of the theorem. We will prove the theorem for n equals 2 and n equals 3, and all the ideas will be contained in those two settings. And the general case I will leave as an exercise. So for n equals 2, let G be this group and X be this set. So let me change it. It's not that set. It's 2 cross 1 matrices over Fp. Essentially, it's the same thing, but yeah. So I'll take away the 0 vector from this vector space. So this is a vector space as we commented. Just take out the 0 vector from it. So that's our set X. It's like the punctured vector space. And then we define an action. So define an action of G on X as G dot X is just the matrix multiplication of G and X. So G is a 2 cross 2 matrix and X is a 2 cross 1 matrix. So it makes sense to multiply the two things. So that's what g dot x is, and one should check that this is indeed an action. The point is that since g is invertible, g dot x cannot fall outside x. X is a non-zero vector, and since g is invertible, this is also a non-zero vector. So that's why this is an action. And the key point is that this action is transitive. So let me justify that. So to show transitivity, let a comma b be an arbitrary element of x. And since this is a non-zero vector, we can extend it to get a linearly independent, we can extend it to get a basis of x. I shouldn't say basis of x, we can extend it to get a basis of this vector space. So let this column be such that, so this is in, again, 2 cross 1 f, be such that these two things are linearly independent. Are linearly independent, and thus this matrix is invertible. And note that, and therefore, if we multiply this matrix A, B, C, D with 1, comma 0, what we get is AB. So we had an arbitrary element in the set X, and we are able to see it as something lying inside the orbit of this vector. So what we have shown is that the orbit of X, the orbit of 1, comma 0, the orbit of 1, comma 0 is the entire set X. So that's we have shown, and that's what we have shown, and therefore the action is indeed transitive. Okay. So let us have a convenient notation for this particular 2 cross 1 matrix. This is an element of X, and we'll denote that by x naught. And yeah, so what we've just noticed is that the orbit of x naught is everything. And now what is the stabilizer of x naught? So the stabilizer of x naught is those matrices. Now do not confuse. Okay, let me not use this notation. Maybe I'll use alpha, beta, gamma, delta. Alpha, beta, gamma, delta. Those matrices in GL2FP such that if you multiply this with 1, comma 0, you get 1, comma 0. That's exactly by definition of the stabilizer. So this is nothing but those 2 cross 2 invertible matrices over FP such that alpha equals 1 and beta equals 0. Because if you multiply this, what you will get is alpha beta. So that's what this multiplication is, this 2 cross 1 matrix. So alpha must be equal to 1 and beta must be equal to 0. So that's what this is. So this is equal to those two cross 2 matrices over FP such that determinant of this is non-zero. Now what happened? So stabilizer is all those matrices in GL2, all those invertible matrices, 2 cross 2 invertible matrices over FP such that this condition holds. So I can write it slightly differently. I can say it's all those 2 cross 2 matrices over FP such that their determinant is non-zero and alpha is 1 and beta is 0. So that's basically this thing. This set is of course equal to that set. But what is the determinant? The determinant is delta. It's just delta minus 0. So it's delta. So let me just write that delta is non-zero. So that's what the stabilizer is. And therefore, the size of the stabilizer is what? Here you can choose any non-zero thing from FP, and here you can choose whatever you want from FP by this characterization. So the size of the stabilizer is P minus 1 times P. P minus 1 choices for delta and P choices for gamma. Okay, I need an extra page. So now that we know the stabilizer, we now use the orbit stabilizer theorem. By the orbit stabilizer theorem, we know that the cardinality of the orbit of x naught is equal to the index of the stabilizer of x naught, which implies cardinality of x, because the orbit of x naught is just the same thing as the set x, and this is equal to that, which implies the cardinality of x times the cardinality of the stabilizer of x naught is the cardinality of our group G, which is this, which implies cardinality of x is what, p, sorry, not p, it's p minus 1. Sorry, it's p square minus 1, because it's 2 cross 1 matrices and then you puncture it. And this is, as we noticed, p into p minus 1. So this is equal to the cardinality of the group that we want. And that means this is equal to p square minus 1 times p square minus p, which matches with what we have written here. For n equals 2, this is exactly what you get. So we have done it for n equals 2. And now let's do it for n equals 3. So for n equals 3, it's the same thing. Here we have the group is GL3FP and X is all 3 cross 1 matrices over FP, and you take out the 0, 1. Right? So it's the punctured 3-dimensional vector space over FP. And then we have the same action that we had previously, just the matrix multiplication action. And this is also a transitive action. I leave you to justify that. It's the same justification. So this is a transitive action. And in fact, yeah, so let x not be this particular guy. Thus, since it is a transitive action, this is equal to everything. The orbit of x naught is everything. Now, what is the stabilizer of x naught? So the stabilizer of x naught is, yeah, so let me use ABC, doesn't matter, A, B, C, D, E, F, or yeah, so A, B, C, D, E, F, G, H. I don't like to use I, but I will. All those things over GL3FP, in GL3FP, which when you multiply by x naught, you get x naught, where again this is A, B, C, D, E, F, G, H, I. But then again, if you multiply this out, you will get A equals 1, B equals 0, and C equals 0. Because if you multiply this out, you will get just this A, B, C, this. Only the first column will be extracted out. So I'll directly write this as A equals 1, B equals 0, and C equals 0, which is nothing but A, D, G. So, okay, 1 DG, 0, 0, E, H, F, I in GL3FP, such that the determinant of this fellow is non-zero, which is to say the same thing as 1 DG, 0, 0, E, H, F, I in GL3FP, where what is the determinant? The determinant of this matrix is same as this determinant, because all of those other parts will go to 0. So this is just determinant of EHFI non-zero, which is same as 1 DG 0, 0 EHFI GL3F. Sorry. Here I meant to write M3. That's what I meant. Sorry about that. This is M3FP, such that this matrix EHFI is in GL2FP. Right? Non-zeroness of the determinant is same as saying the matrix is in GL2FP. So now what is the stabilizer? For the stabilizer, you can choose whatever you want in place of D and G. And here you are constrained to choose an invertible matrix, an invertible 2 cross 2 matrix over FP. So the size of the stabilizer is P choices for D, P choices for G, and then the cardinality of GL2FP to fill this part. But we have already calculated the cardinality of GL2FP. So that cardinality is P square minus 1 into P square minus P. So the cardinality that we computed earlier is useful. So n equals 2 is useful for n equals 3. So this is an inductive step. Alright, and now we just use the orbit stabilizer theorem as before. So by orbit stabilizer theorem, the size of the orbit of x is the index of the stabilizer, which implies p cube minus 1, because orbit of x naught is the entire set x and the cardinality of x is p cube minus 1. This is equal to size of g divided by the size of stabilizer, which gives p cube minus 1 times the size of stabilizer, which we just computed, is what? P square times p square minus 1 times p square minus p. This is the size of g, which is the same as GL3FP. But this thing is nothing but p cube minus p and p cube minus p square, because one of these p's will go inside here and the other p will go inside here. This is equal to cardinality of GL3FP. That's it. So this inductive step will come if you're writing the proof for general n. You'll see the same kind of thing. Here you'll see GLN minus 1 FP, and here you will be free to choose whatever, and it's the same proof. Okay, so sorry, I messed up here. When I came here, I should have written M3, but I just wrote. When I came here, I wrote GL3, but I should have written M3. I hope you did not get confused. Okay, so this is it, and I'll see you next time.